Newton's first law dictates that an object in motion stays in motion. An object not in motion doesn't stay in motion unless there's a force applied to it.
Newton's second law of motion explains how an object will always change velocity when you push or pull it. This law states that if you do place a force on an object, it will accelerate, or it will change its velocity, and it will change the velocity in the direction of the force exerted on it.
Computer with logger probe.
Metal stand that supports force sensor. Force sensor. Many weights.
Elevator.
Place two weights on the force plate stand. This will be used to measure the increase and decrease in the mass. Then place it inside the elevator to conduct the experiment.
Now you're at rest. Push 2 to go up in the elevator and find the change in forces. Repeat the steps with different weights. I'm at rest. It seems like I'm getting heavier. It seems like I'm getting heavier than before. I'm at rest again. This is a force graph from one of our trials. When the elevator hadn't moved, the weights were at rest. They weighed 6.02 newtons and had a mass of 0.62 kilograms. As the elevator went up, it had a positive acceleration. At this certain point, the object or weight had a constant acceleration. This point is also called the lift force. This force is 6.36 newtons. This certain part meant it had negative acceleration. During this time, the weights seemed as if they had less weight or losing weight. When the object or weight reached its last point where the elevator stopped, it was at rest again.
This graph shows net force versus mass. Net force equals mass times acceleration. Acceleration equals net force divided by mass. The slope of this graph is the acceleration, and the acceleration is 0.4105 newtons.
These graphs show the 7 different masses we used in our experiment. It indicates the change in forces when the weights went up the elevator.
Our independent variable in this experiment was the different weights. Our dependent variables were the same elevator, the same people, the same force plate, the same computer, and the same time.
Our table shows the average weight, the average mass, the average lift force, and the average net force from each and every graph we made. Observations. We observed that when the elevator was at rest, we felt the same weight. When the elevator was going up, we felt heavier. When the elevator was about to stop, we felt less heavy. But when it stopped, we felt again our normal weight.
These are the formulas that we used in our experiment to conclude our data. In it, we have included some specific examples of each. Newton's second law dictates that force equals mass times acceleration, or in other words, acceleration equals force times mass. This means that as the elevator went up, we felt heavier because the net force was increasing. When the elevator was in the first floor, not moving, we were at rest because there was no force acting on our weight. At rest means that the weight does not change. When the elevator went up, we felt heavier because the net force increased. This can be observed in the graph because the slope was going upward. In conclusion, the heavier the object was and the bigger its mass, the more net force is required to reach the same acceleration. Sources of error. The air slightly moved the weights. Our slight movement was out of our control. The elevator might not have the constant movement needed. Possible improvements were to try to do it with less people in the elevator, and that when collecting the data, we could have had the weights